This is Nereid, an interdisciplinary approach to detect bacteria in water using microscopic images for early detection of waterborne disease. 2.5 billion people lack access to clean water, and an estimated 1 out of 3 drinks from such severely contaminated water that they are at severe risk for waterborne disease. This issue ranges from both developing countries as well as developed. It is crucial that we find an early and effective solution. The current solutions on the consumer end, there are water-based test kits, which are highly expensive and can be inaccurate. On the municipal end, there are no further checks for bacteria detection once water enters the distribution system. I wanted to find a solution, and my initial idea was to use microscopic images and analyze them for the presence of bacteria. I decided to use a neural network to aid me in this process. My success criteria were: the network had to have an accuracy greater than 90%, be able to classify the various combinations of bacteria, and be a fully applicable model. I started off my process with the collection of my data. I did not have access to a laboratory environment, so I decided to use non-toxic bacteria, such as Lactobacillus, Streptococcus thermophilus, and Saccharomyces cerevisiae. I created various solutions of these bacteria and took 3,000 images, separated in a 2-to-1 ratio for training and testing. Then I moved on to data augmentation. I wanted to make sure that my images had the highest level of clarity possible. And sometimes, in some images, there was Brownian motion, where due to the natural tendency of liquids, the water shifted on the slide, leading to blurry images. To mitigate this issue, I used a median filter and a sharpness filter to ensure the highest level of clarity. Here is a before and after, and you can see the difference. Then, I moved on to feature extraction. The features extracted were what I wanted my device to focus on, not background noise. I decided on 2 main features, the first being bacteria shape. For example, Streptococcus thermophilus is a cocci, or circular-shaped bacteria, whereas Lactobacillus is a bacilli, or a rod-shaped bacteria. The other feature was bacteria size. For example, Streptococcus thermophilus is a very small bacteria at about 0.1 micrometers, whereas Saccharomyces cerevisiae is quite large at about 10 micrometers. Now I moved on to the creation of my actual neural network. I created an 11-layer network with 6 different types of layers, including data input, convolution, and feature extraction. From here, I moved on to the selection of my algorithm. The algorithm determined how my network would process. I immediately eliminated some, such as polynomial regression or support vector, because I knew they could not handle such a complex problem. In the end, the decision came down to gradient descent or stochastic gradient descent. I chose stochastic gradient descent because it was able to have multiple peaks of accuracy and was multidimensional, meaning it could support and process such a complex issue. I then had to select a learning rate. The learning rate determines the size of the steps my program takes from one point to another on the descent. Too large means the optimum point is missed, whereas too small means that the program gets stuck in a valley. After testing, I chose a learning rate of 0.01 because it had a high accuracy and medium processing time. Now, with my neural network created, I could move on to testing. In testing, I used the 1,000 previously mentioned testing images that my network had not before seen. I tested it and found an accuracy of 98.13 and a recall or F-score rate of 94.25. As seen in this confusion matrix, it was also able to identify the various classes and combinations of bacteria correctly, meaning it had achieved 2 of the 3 success criteria. Moving on to my final development phase, phase 5 and 6, during which I developed my fully applicable model. To start off with this, I began with imaging setup, where I decided to have an outlet come off of the main water pipe. Water would be pulled into this outlet using a peristaltic pump, which is a pump that uses pressure to pull the water in, reducing the risk of cross-contamination. From here, the water would go onto a laser-engraved reservoir on a slide, where above this stagnant water, there would be the imaging setup. I wanted to create a more affordable version of a microscopic camera, so I utilized a Raspberry Pi camera and a microscopic lens. From here, my camera would take images at scheduled intervals, and a scheduled cron job, C-R-O-N job, would be able to process them and send them to the network for classification. At this classification, I faced a problem. How would I get my classification that the network processed and send it to the water plant where people could actually see them? To do this, I needed a technology that would be able to transfer data over long distances. After research, I found out about the LoRa, or long-range radio methods. This method is able to transfer small amounts of data over large distances, meaning I could utilize it for my neural network and Nereid's program. Using this, I used a 433 megahertz frequency, and on a tested whip antenna, it had a range of about 30 feet. But I'm positive that with more amplitude and a higher and more powerful antenna, I'll be able to increase this distance so that we can have a fully applicable model. The current version of Nereid is much more efficient and affordable than most solutions today. It has a very high accuracy of 98.13 and a processing time of mere seconds. It also has a high longevity of multiple years. But I still want to improve this device. I want to increase my dataset and my database and move to more common waterborne disease such as cholera and E. coli. And I also want to create a GPS mapping system. We're using an IoT or Internet of Things device. I can have constant updates on the app about local water quality, meaning that people can always stay informed about the local water quality in their area. I truly believe that with Nereid, we can change the world. Simply one water droplet at a time. Thank you.